CoqIDE is the graphical user interface for Coq. It has a window which is divided into three areas. This is where you write your Coq code. Over here in this window you will see the goals, the things that need to be proved, and down here is the message area where Coq prints its messages. Just so that we have something to work with, let us show that Peirce's law is equivalent to the law of excluded middle. I'm not going to explain too much of Coq itself here. I'm going to focus on how to use the IDE. First, we define both laws. So this is Peirce's law, if I got it right. And whenever you write a piece of code, you can immediately check whether Coq is happy with it. You say move down, and then if Coq is happy, it will color the piece of code with the green color. So now we have defined both laws. We can prove a theorem. It quickly gets annoying to press this little button here. So in fact there are keyboard shortcuts that you should learn. On my Mac you can move down or forward with, well, it's with command control down arrow, even though what this says here is not correct. You should find out what the correct key binding is. Just experiment with Shift, Control, Alt and all the other keys for a while. So anyhow, on my keyboard it's Control, Command, down, which moves down. You can also move up if you need to fix anything. For example, suppose I wanted to fix this part here, then I can't do it because it was already accepted by Coq. But if I move up, then I'm free to edit. And then I can go back down. This is what they mean by interactive theorem proving. You don't have to write the whole file at once, you just do it step by step. Anyway, let us prove this. So we start a proof. Now you see here Coq is telling us what we need to do. We need to prove this. So for example, we might try a powerful tactic for first order logic, but it's not happy. It says I don't know what to do with this. In fact, what we have to do first is we have to unfold the definitions. Don't worry, you don't have to unfold definitions by hand all the time. You can tell Coq that certain definitions should be unfolded by themselves and so on. So we're not studying Coq now, we're studying the graphical user interface. So now if I try first order, so whenever you see the green part moving down, I pressed Control to Command down. By the way, you can also just go to some place and say move here, which is Control, it's this one. And then the green area moves exactly there. So let's go down here. Okay, now you see it's telling us that there are two sub-goals to be proved. The first one is P or not P. And the things above the line are the available hypotheses. So we have a hypothesis called H, well, which is essentially Peirce's law. And we also have the hypothesis here. You have to be careful here. This doesn't say that P is a hypothesis. This doesn't say that we are assuming that P is true. The only thing we're assuming is that P is a proposition. So how do we do this? First order doesn't know. We have to provide a sufficiently good hint, and the hint is that we should use H with Q being the negation of P or not P. This. Now if I try first order again, it succeeds and the control has gone to the other sub-goal. So now here I have to prove P, and my assumptions are H, which is the law of excluded middle. There is a P, which is a proposition. Again, this doesn't mean that P is true, it just means P is a proposition. Q, which is a proposition, and H0 is a proof of P implies Q implies P. So there are two ways you can read this. You can say, well, I have an assumption called H0, which states that P implies Q implies P, or you can say H0 is a proof of P implies Q implies P. Anyway, in order to finish this proof, what we do is, again, we use our hypothesis H, and so we, in this case, we use a slightly different technique. We say apply H to P and destruct, which means it will make it consider two cases. And now here are the two cases. So this one is easy, where I'm trying to prove P, but I have the assumption P, so I just tell Coq, well, this is an assumption. And here we have to prove P, but we have not P. So I might just get lazy and I say, well, you figure it out. Use a tactic. T-auto is a tactic which can handle propositional tautologies. And that's it. This is our first proof.